Hi everyone, we'd like to present our group project for assignment 2. And our topic is Generative Recommender System on Amazon Musical Instruments dataset. And our contents can be roughly divided into 6 sections: Introduction and Motivation, Dataset Analysis and Preprocessing, Baseline Modeling and Evaluation, Tiger for Generative Recommendation, Final Evaluation, and Further Improvement. Let's move to the first part. So our task is sequential recommendation task. To be more detailed, for each user, we will predict the next item based on previous interaction history, and it is a kind of implicit feedback. And we can see modern research focus have shifted to this kind of sequential recommendation task rather than traditional explicit feedback like rating prediction. But we found that traditional recommender systems like matrix factorization suffer from two main limitations. For one thing is code start problem. They cannot recommend new items without interaction history. And for the other, they lack of semantic understanding. For example, they will treat guitar and guitar strings as two independent IDs, ignoring their inherent semantic connection. So the model we used is Tiger. It will address this by encoding items into semantic IDs, use a pre-trained sentence bird encode and residential quantization, then training a sequence-to-sequence transformer to predict the next semantic ID based on user history, effectively treating recommendation as a link generation task. And we'd like to summarize our contribution. First, we implement and evaluate Tiger, that is Transformer Index for Generative Recommenders, a SOTA generative recommendation framework. Then we apply this framework to Amazon Review's 2023 musical instruments and compare its performance against two strong cost-relevant baselines, Markov chains and BPR-MX. Last, we also propose a hybrid criteria based on uncertainty score threshold to choose which model to predict the latest interaction. And we like to talk about the related work. First is the dataset we used, the Amazon Reviews dataset on musical instruments. It is a widely established benchmark in sequential recommendation research. First, it has high sparsity, almost 99.9%, and strong sequential dependencies. Like for example, a user purchasing a guitar is likely to subsequently purchase strings or keys. Unlike movies or books datasets, the user tastes are broad, so interactions in musical instruments are often goal-oriented and temporally clustered. On the other hand, they follow such a preprocessing standards. Prior work will typically apply 5-core filtering, that is to say remove users or items with fewer than 5 interactions. It can guarantee the sufficient history for modeling sequential paths. Then we will move to related models. A kind of popular models is static representation learning, like BPR-MF. It represents more users and items as static embeddings and model preference via dot products. But it has a very obvious limitation that this model treats user history as a bag of items, ignoring the order of interactions. Another kind of model is transition-based sequential models, like Markov chains. They model the transition probability matrix between items, like calculating p(i)t plus 1 contingent on it. The advantage is that they capture immediate sequential signals, like from camera to SD card, but we need to extract stronger information from short sequence. And the last kind of model is generative recommendation system with semantic IDs, like Tiger, what we used. It redefines recommendation as a sequence generation task. Instead of atomic integer IDs, they utilize semantic IDs derived from item content, like titles or descriptions using RQVA. Then it allows the model to understand that a Fender Stratocaster is semantically similar to a Gibson Les Paul, even if they haven't met each other. This transfer learning capability addresses the cold start and long tail problems inherited in sparse datasets, and experimental results at last outperform previous methods a lot. Then we will move to the dataset section. First, we use the Amazon Review dataset, and we can take a look at the two examples of both metadata and interaction. For metadata, we have title, categories, features, and description. And for interaction, we will record the user ID, item ID, timestamp, and rating. Then, in order to build a sequential next item prediction task, we will build a user behavior sequence, first by time sorting. And like what we are mentioning in related work part, we will also apply the recursive 5-core filter, remove users and items less than 5 interactions in order to ensure enough history for meaningful sequence modeling. Then for sequence construction, we will first sort the interactions chronologically for each user, and then use a leave one out split. We treat the last item as the test target and others as the training one. It can prevent the data leakage and mimic real-world recommendation scenario. We also conduct some exploratory data set analysis. First, we investigate the distribution of the real-time data. As is shown in the figure, we can say most data is primarily concentrated in the later periods, like higher timestamps, indicates a trend of gradual growth over time. So this kind of temporal dynamics suggests that we need to consider the evolution of user interest over time. And this temporal distribution also supports the importance of using sequential models to capture users' recent interest. And when it comes to product ratings, we found that the distribution is an extreme negative skew. The vast majority of ratings are concentrated on the highest score of 5 stars, then followed by 4 stars and 1 stars. Other scores are very, very rare. So we can say users on the Amazon platform primarily tend to give positive feedback. And if we only rely on explicit feedback like ratings, this may not be effective in distinguishing subtle preference differences among users for various items. We also investigated the sparsity, and as you can see in the 2 graphs below, the first one is the distribution of items per user. We call it user activity. And the other is users per item distribution, and we call it item popularity. And we found that these 2 graphs have a very similar trends. The vast majority of users have only interacted with a very small number of items, less than 5, and only a small number of super users possess a large volume of interaction. Also, the vast majority of items are only purchased or reviewed by a very, very small number of users, with a few popular numbers account for a large number of interactions. And now, if we scale the y-axis of the user activity of the item popularity distribution, we will have the same trend. And first, we observe the very highly long-tail item distribution. That is to say, top items cover large share of interactions. Like here, top 5% items cover 38% of interactions. So a pure popularity-driven baseline will perform reasonably well, but might fail to model personalized or sequential preferences. And last, we also investigate the user sequence length distribution, and we can find that these user interaction histories are quite short. The mean sequence length is only 9. So most users have short but informative sequences, and short patterns are likely very important, and event-based sequential models, like Markov chain.
Now let me briefly walk through the evaluation metrics. We evaluate performance using recall and normalized discounted cumulative gain. Recall is a simply hit rate style metrics. Recall at 10 tells us whether the correct next item appears in the top 10 list, while NDCG measures the ranking quality of the recommendations and rewards the correct item for being ranked high. In other words, more sensitive to ordering. Higher rank leads to higher NDCG. These metrics stand for evaluating ranking-based recommenders and allow us to compare all models under the same conditions. So now I'll talk about baseline modeling. Our first baseline is Bayesian personalized ranking matrix factorization, which captures long-term static user preferences. It learns a latent factor representation of users and items using a pairwise ranking loss, aiming to rank interacted items higher than random negatives. However, Bayesian personalized ranking matrix factorization ignores the order of interactions completely. Every interaction is treated independently, so although it captures stable preference structure, it cannot model short-term dynamics, which are very important in our dataset, where sequences are short. This baseline gives us a static preference reference point. Our second baseline directly models short-term sequential transitions. Our first-order Markov chain calculates transition probabilities between consecutive items. During prediction, we take the user's most recent item and recommend the items with the highest transition probability. This baseline focuses entirely on short-term patterns, which aligns well with the user sequence length distribution we saw earlier. It ignores user identity, but leverages the strong tendency of users to interact with related items in quick succession. So we have two very classical baselines that capture very different aspects, both short-term and long-term, of user behavior, so we can have the earlier evaluation. Here's the baseline performance comparison plot. In the bar charts, each model has two bars, one for recall and one for NDCG. Numerically, the Markov chain achieves a recall at 10 of about 0.054, whereas BPRMF is around 0.034. NDCG10 also shows a similar pattern, so the Markov chain consistently ranks the correct next item higher than BPRMF. This gap is quite meaningful. It tells us that in this musical instruments dataset, short-term sequence information is more predictive than purely static user performance. So even though BPRMF is a strong traditional recommender, it lags behind a simple sequential model here. This resource provides a clear motivation for using a more powerful sequence-aware generative model like Tiger, which is designed to leverage these transition patterns even more efficiently. So now we'll introduce Xiaofang to explain generative recommendation Tiger.
Okay, thanks. Now let's dive into the core of our project, the Tiger model, which stands for Transformer Index for Generative Recommenders. It is basically an RQVE followed by a transformer. To understand Tiger, we must first find out the evolution of item encoding. Traditional autoencoders are good for compression, but bad for generating new content because the latent space is irregular. Then we have a variational autoencoder, which introduced probability distributions to make the space continuous. But transformer need tokens, not continuous vectors. That's why we use residual quantized VAE. It quantize the latent space into a tuple of semantic ID. And then why do we need to use Tiger approach? Why do we choose it? Looking at our two baseline, BPRMF is static and missing the sequential information entirely. Markov chain captures short sequential information but treated the item as meaningless number. Our core model, Tiger, used transformer for long-term context and construct semantic ID from item metadata, which combine the advantage of these two baseline and can make it much powerful than our two baseline. But it seems like native transformer already have these two good features. Why not just use Robert embeddings? Why we have to use RQVE? This answer lies in two properties of the two properties given by the RQVE in our feature space: continuity and then completeness. So what is continuity? Continuity means two adjacent points in the latent space produce similar content after decoding. Lack of continuity in recommendation scenario means that small change in input can lead to dramatic change in the output, usually lead to bad generalization capability on unseen data space. Second, completeness. It means that for a selected distribution, points sampled from the latent space should produce meaningful content after decoding. Without completeness, model is easy to produce meaningless prediction. In Tiger, it means predictive semantic ID cannot be mapped to any item in one word. RQVE brings us the essential nice feature we need in the feature space for generative recommendation. After go over all this theoretical foundation, let's look at the overall architecture for Tiger. The Tiger system has two phases, encoding phase and generating phase. Let's go through them one by one. Let's focus on the encoding phase first. So the encoding phase is the RQVE. We start from the raw text and then pass it through a pre-trained T5 BERT to get a continuous embedding. Then the RQVE will take this continuous vector and map it to the nearest discrete code in our codebook. So how does this mapping work mathematically? Let's look at the formula. First, we find the closest vector to the original input. That will be our first code. Here is 7. And we calculate the residual error. And in the next round, we quantize only the error. That will be our second code. Here's 1. And we repeat this procedure. In the end, get 3 number, 714, which is the semantic ID for our input item. While developing the pipeline, we also did some analysis. We analyzed the repetition rate for semantic IDs of the next levels of, the next item prediction at different fine-grained levels. The 3 lines in the graph represent 3 different levels of semantic representation. This virtualization proves that first, semantic IDs effectively captured users' long-term preference trends, and second, semantic ID captured hierarchical similarity between items. This basically tells us that semantic ID is a really powerful representation for our item. Let's simply go over the code now. So here's our tiger model. We start from here and did some data preprocessing. And first we processed and map item to a semantic ID. And we also did some analysis here, as you can see on the slides. After we finish the encoding part, we goes to the generalization part. So there will be let's go back to the slides. There will be the sequence-to-sequence model, the transformer. Now the phase 2, we use the standard transformer architecture. During the inference, it works like a translator. Let's look at the example. The transformer gets input of a sequence of semantic ID and auto-regressively predicts the next tuple. So in this example, the first token is 5 and token 25, and then token 55. In the end, we will map this generated tuple to item 64, which will be used for recommendation. Let's go back to the Jupyter notebook and just a short review. We start our transformer model definition here, and we did some training procedure. So the whole training takes us about 21 hours. So it's a really heavy work, and then after the training, we did some evaluation. Let's go back to the slides. So how does our model perform? According to the experiment result, our generative solution smashed the two baseline. Our tiger model achieved the highest recall score of 0.05, significantly outperforming both baseline. In terms of ranking quality expressed in NDCG score, tiger also performed really well, 0.03. But we didn't just stop by just beating the baseline, we did much more than that. Let's look at the concept of sampling. Theoretically, optimal sampling wants to pick the sample with the highest joint probability globally, but this is impossible because we can't enumerate all the results. So people invent some alternative approach. For example, greedy master or top K for LM serving, and then in recommendation scenario, we always use beam search. Or the sampling method implicitly tells us that logistic output tells us how certain the model with a given answer. So we propose an hypothesis called high uncertainty trap. It is basically saying when model is not sure about its answer might be wrong. And when falling the trap, we can try some other general model which may get a better answer. How do we identify the trap? We can't just simply multiply probability score because low confidence doesn't always equals to high uncertainty. We are not going to explain too much detail about that. You can check the ARM uncertainty study if you want. So if this hypothesis true, we just propose it, but we need to formally prove it. To address model uncertainty, we tried a lot of metrics and selected the metrics called self-certainty score as our confidence metrics. As you can see the formula list here, and we analyzed the self-certainty against NDCG accuracy in each sampling layer. As you can see from the diagram, the higher the certainty, the better the accuracy. This means our hypothesis is true. The high uncertainty trap does exist. So how do we escape from this trap? We have a hybrid idea. Is to switch model when uncertainty score fall down the configure threshold. We tried alternative models like native top K and item-based coverage filtering and tuning the threshold. As you can see on the right-hand side, our solution improved over the pure tiger when we switched to a simple item-based coverage filtering for the bottom 1% of the most uncertainty sample. This indicates that confidence estimation can help build a hybrid solution way beyond any single model, although it is powerful enough, just like our tiger model here. So to run through the code again, we did this extra part right after our evaluation. As you can see, we tried different metrics, did the analysis. Also, we have tried different alternative model. We also tuned the threshold here. And in the end, we get our final result, as you can see on the slides. Okay, let's wrap up our presentation. So we will end with some inspiration and comparison. Just for taking away, first, RQVAE is a powerful encoding technique in recommender system. And second, transformer can perform well in many fields as long as it runs in heavy quality feature space. Third, model uncertainty and performance are interrelated. Uncertainty study can be used for optimized performance. We also compare our performance with related works. The original Tiger paper is trained and tested on a subset of sport, beauty, and game in Amazon Review 2023 dataset. Record score from 0.04 to 0.07. And city score from 0.02 to 0.04. Our model is experiment on the musical instrument subset and get a record of 0.05 and any city score about 0.03. This tells that our model did a good job and can match the performance of the related works. This is all for our presentation. Thanks for listening.